Welcome to the new and highly improved version of the NRPSDesigner. In this video tutorial, I'd like to show you what the NRPSDesigner does and how you can use its core functionality. In order to get started, you can either choose this app here or just click on this Design New NRP button. Now, the idea behind the NRPSDesigner is the creation of novel, synthetic, non-ribosomal peptide synthetases, which can produce a peptide of the user's choice. Down here, a user can easily choose a monomer, the monomers out of which his final peptide should consist. For example, let's choose alanine for the first position, and for the second we might choose hydroxyphenylglycine and also its D configuration. Note that this is already interesting because it's a non-proteinogenic amino acid and also its D form. And let's also make a tripeptide. Let's choose serine for this third position. And now that we've done our choice, here you can see a visualization of the chosen peptide. You can click on Design Construct. Now, based on the NRPSDesigner database, our algorithm calculates a sequence of domains which could produce the peptide of choice. Here you can see those domains. Then we move to the next layer of biological hierarchy, to the actual DNA and the fragments that have to be assembled in order to get a functional synthetase. The 5 fragments shown here would have to be amplified, for example by PCR, and then assembled together. For example, let's look at this longer fragment. This is called by this Streptomyces species, so you could actually amplify this whole fragment coding for 4 domains out of this one species. Of course, beyond the functional synthetase, in your final plasmid you also want to have a backbone, so you can add this as well. What is very important to note here is that beyond standard backbone features such as antibiotic selection marker and an origin of replication, you also need a promoter, ribosome binding site, and more importantly an start and stop codon. So before the initiation domain you need to ensure that your construct has a start codon, and directly after the thioesterase that you add the stop codon. I'd like to mention at this point that in our experiments during iGEM we assembled those fragments mainly using Gibson assembly. For this reason the view you see here is based on Gibson, on a previously published software which makes this cloning method very easy. And one of its outputs is a sequence of primers that can be used for this assembly method. For this we need to go to the next tab and design our primers. Now Gibson actually uses Unafol to calculate some statistics for the calculated primers. And then we get this output here. Here you can see a primer summary of all the primers that will be needed in order to assemble the parts, and you can also click at particular primers to see the exact sequence. Notice also that you already get some of the Unafold warnings. Still, you can actually modify the primer, for example make it longer or shorter. Once you've made all your selections regarding primers, you can press this button and you get a zip file which actually includes all primers in a CSV file. You also get a SBOL and GenBank file which contains the sequence of this synthetic synthetase. Those files can also be downloaded here.